Assalamualaikum and greeting everyone. Welcome to my final year project presentation. My name is Afra Balkis binti Hafiz, a final year student in Bachelor of Science Horns Biology. The title of my FYP is The Physical and Chemical Properties of Kenaf Empty Fruit Bunch Fiber Reinforced Polylactic Acid PLA Composite in University Technology Maharashtra Alam Campus. I am supervised by my lecturer Dr. Siti Hasna binti Kamarudin. First, let's begin with overview. For introduction, consists of background of the study, problem statement, objective of the study. After that, methodology, result, discussion, reference, conclusion, and recommendation. Next, introduction. According to the Secure et al. 2020, sustainability and the depletion of petroleum resources have led to the development of sustainable and environmentally friendly products. Natural fibers such as Kenaf, cassava, oil palm, cotton, hemp, and coir offer superior properties such as high specific strength, lightweight, and low cost, stated by Al-Subairi et al. 2021. Thus, it is important for the researcher to fully utilize natural type of fibers such as Kenaf and AFB fiber to be combined with PLA polymer matrix in order to produce Kenaf AFB PLA composite for use in various types of application and testing. Goals of SDG that have related with this thesis: quality education, affordable and clean energy, sustainable cities and communities, and climate action. For background of study, Mekala et al. 2019 have stated that Kenaf fiber, a fast-growing plant, is a significant source of fiber for composite and industrial application. It has habit non-abrasiveness and biodegradability. Polylactic acid PLA is renewable polymer derived from biomass and is widely used in packaging and the medical industry to replace petroleum-based plastic by Ochi et al. 2018. Filler that have been used are Kenaf and empty fruit bunch. Problem statement consists of two problems. First, plastic pollution, and second, drawbacks of Kenaf and FB natural fiber. Kenaf have poor compatibility between the fiber and the polymer and high humidity, while EFB have high oil content and contains waxy layer on the finer surface. Methodology: Kenaf and FB will undergo treatment with 6% of sodium hydroxide solution at room temperature for 3 hours. Then fiber will dry in an oven at 18 degrees Celsius for 3 hours according to research by Muhammad et al. 2050, Nasidi et al. 2018, and Kamarudin et al. 2020. Next, biocomposite of Kenaf FB PLA were prepared by internal mixer. PLA grains are thoroughly and uniformly combined with both fiber. The ratio of Kenaf FB PLA is 50% by weight, 15% by weight, and 70% by weight, respectively. The composite is molded using a hot press machine at temperature 119 degrees Celsius for 5 minutes. The composite is then cooling at 27 degrees Celsius by Islam et al. 2050. Determination of physical properties by doing density testing by using electron decimeter machine. Next, determination of chemical properties by doing alkaline treatment and Fourier transform infrared. For alkaline treatment, fiber was randomly sized in 3 mm to 3 mm submerged in 6% sodium hydroxide solution for 3 hours at room temperature. Then cleaned under running water by using distilled water repeatedly to neutralize the fiber. Lastly, put in the oven at 100 degrees Celsius, stated by Fire et al. 2050. For FTIR testing, have been running to look out to the chemical structure and get morphological data from functional group, composition of chemical, and bond type of composites. Determination of morphological properties by using scanning electron microscope. The morphology of the fracture sample from physical and chemical tests has been analyzed using scanning electron microscope. Result and discussion. First, for density testing by looking at the table 1 and graph 1, the graph show density slightly decreased and increasing for the last bar, which represent of Kenaf FB PLA composite with density 1.337. Generally, the introduction of filler affect the density and free volume of the polymer chain. Free volume can be increased by the combination of decreased molecular weight and increased chain mobility. Therefore, increased filler concentration increased free volume, hence leading to the density reduction visible in the graph 1. Low density lead to the lighter weight composite. Second, scanning electron microscope display SEM image of the tensile crack surface of composite made of FB PLA, Kenaf PLA, and FB Kenaf PLA. Following fiber hybridization, there was an increase in surface contact and adhesion between the fiber and polymer matrix. The hybrid fiber composite micrograph show no discernible alteration. However, the hybridization of two fibers resulted in a smooth broken surface, demonstrating strong fiber adherence to the polymer matrix. Improved polymer matrix and fiber adhesion is essential for improving the mechanical characteristic of composite. This outcome demonstrated the increase in mechanical strength caused by fiber hybridization. Third, alkaline treatment in table 2A and B. The chemical composition of Kenaf fiber and FB that have been treated and those not been treated are compared. The NaO treatment was successful in eliminating the lignin and hemicellulose from the Kenaf and FB fiber, as the lignin content dropped from 70 to 14% for Kenaf fiber, while for FB fiber lignin content dropped from 20 to 30%, and the quantity of hemicellulose dropped from 21 to 50%. and from 25 to 40%. The cellulose content increased from 51 to 56% and from 38 to 46%. It is known that Kenaf fiber and FB characteristics were more strongly influenced by their cellulose concentration. In other words, the stress transfer between fiber will be larger when the cellulose content higher in the fiber, which ultimately support the higher mechanical properties of the composite. By removing both natural and manufactured contaminants, the alkaline treatment modification had improved the fiber surface adhesion, which improved wettability between fiber and matrix. Natural fiber that have undergone chemical alteration have had the hydrogen bonding in the network structure disturbed, enhancing the surface roughness of the fiber. This helped the treated Kenaf fiber and FB fiber surface morphological properties to improve when compared to the untreated Kenaf fiber and FB fiber. For FTIR, as displayed in graph 3b, in the range of 3,200 and 3,600 cm1, a broad peak is attributed to OH trenching that may be caused by leading group in the Kenaf core. Additionally, the production of hydrogen bonds causes a OH peak to shift to lower wave number and broaden. When observed, this peak grew a little bit wider when PLA Kenaf core content increased, supporting the growing hydrogen bonding between the matrix and filler by Nazila et al. 2013, as shown in figure 3c. The untreated Kenaf and FB show a strong peak at 1636.63 and 3458.36 cm-1, representing the C-O and OH group respectively by Lee et al. 2017. The spectrum of treated fibers show that the peak of C-O 1736.26 cm-1 and CO 1245.35 cm-1 disappear after undergoing treatment with alkali solution. Conclusion: the physical property, for example, by doing density testing, can determine the difference between density of untreated fiber with the treated fiber. The chemical property, for example, by doing the alkaline treated, improve the surface of the fiber, and doing FTIR, we can see the OH hydroxyl group and CO group for ester in treated Kenaf FB fiber show broader and less strong peak as compared to untreated Kenaf and FB peak. Propagation in the future. Continued research and development in this field may result in the development of biocomposite materials that are even stronger and more effective than currently available materials, while also being more sustainable. For the potential application, this biocomposite can be used in the future as packaging and building. That's all from me for my final year project presentation. Thank you.